Hi friends, welcome again. In our last video, we saw how to configure the STM32 Nucleus 64 and we wrote a small program to toggle one of the GPIO pin which is connected to the LED and we wrote few instructions to toggle the LED at some particular frequency. Today, we are going to see what are the other GPIO features available with STM32. Then we will understand the various GPIO configuration registers, and at the end we will make one GPIO as input which is connected to the onboard push button, and we will do a program to toggle the LED or switch on the LED when the button is pressed, and when release the button we will just switch off the LED. So let us go and see the features available with GPIO. So first is push pull or open drain plus pull up pull down. So we'll go in detail what is push pull, open drain, pull up and pull down. Then we have output data from output data register. So output data register is one register where we have to write something which we want to provide to the output. So we can read that to verify. So sometimes we need to verify whatever we are writing to the output is correct. So there is output data from output data register. Then speed selection for each IO. So you can select the speed for each of the IO, low speed or high speed. Input states. So these are the available input state. Floating. We'll go through what is floating, pull up, pull down. Then analog. So then input data to input data register. So input data register is one register where we can read the input of each of the IO. So where the data register will be updated by the input, and we need to read that register to get the input status. Then bit set and reset register, that is BSRR or bitwise write access to GPIOs. So whatever output data register we have, so that we can access bitwise if we'll set this BSRR register. So we don't have to update the whole port. So we can each of the pin we can set or reset. Then locking mechanism to freeze the IO port configuration. So sometimes we need to lock the configuration once our program is started and we configured all the GPIO. We need to lock it so that any bug in our program will not modify that configuration. So locking mechanism is there to overcome unintended configuration change. Analog function, as we already saw here, analog input is there. So based on the IO pin, some of the IO pins support analog function. Alternate function selection. So there are a range of alternate functions for specific IO pins, so that we can choose from. Fast toggle capable of changing every 2 clock cycles. So as we saw here, the speed selection for each IO, we can go for high speed, which can capable of changing every 2 clock cycles. So this we can toggle the IO pins as fast as every 2 clock cycles. Then highly flexible pin multiplexing. So as we saw, some of the pins are having some alternate function, then analog function. So the multiplexing allows us to choose IO pins as GPIO or any other different function. Now coming to the push, pull and open drain configuration. Here we have the circuit for push, pull and open drain. Left side is the push, pull configuration. Here there are two FATs, one is PMOS and other is NMOS. Both the gate of both the FATs are connected together to form the input, and the drains of both the FATs are connected together to form the output. While the source of P MOS is connected to the positive rail, that is the VCC, and the source of NMOS is connected to the ground. Okay, so here is one inverter which invert the signal from the CPU while it is going to the gate. So here what happens when the CPU will write 0 over here, it will be converted to 1, which is applied to both the gates, and when it is 1, the PMOS will be in non-conduction mode, that is it will cut off the VCC with the drain, while the NMOS will be in conduction mode. So now if you'll see, the ground is connected to the drain, which is in turns the GPIO pin, output pin. So now the at the output we will get a 0, that is the ground is connected here, we will get a low logic here. Okay, but when the CPU will write 1 here, the inverter circuit here will make it 0 over here on both the gates. Now the NMOS will be in non-conduction mode, it will not conduct now, and PMOS will be in conduction mode. Now the VCC or the positive rail is connected to the drain, which is the GPIO output pin. So now if you'll see, the GPIO output pin will see the voltage whatever is there at the positive rail. So we'll get a high logic here. So in short, when we're writing here 1, PMOS will be in conduction mode, and at the output we'll get a high logic. When we'll write here 0, NMOS will be in conduction mode and we'll get a low logic at the output. Why it is push-pull? Because when we are giving it 1, the current is going from VCC through the drain to the output pin. So current is going from the circuit to the output pin. So current is going out, current is being pushed from the pin, output pin. But when it is a low logic, when we will write it 0, so the GPIO pin is in low logic, so now current will be pulled inside the circuit. So now current will flow from the input pin through the drain to the ground. So current will be pulled inside the circuit. So that's the reason it is a push pull. So now we'll see the open drain configuration. So in open drain configuration, what is done is this PFET, PMOS is removed. Now only we have the NMOS circuit here. Here what happens, when the CPU will write 0 here, it will be inverted and it will made a 1 here. So as we know, if it is 1, the NMOS will conduct. So now when at the input here it is 0, NMOS is conducting, and the output, that is output pin GPIO, which is connected to the drain of the NMOS, will be connected to ground. So we will get a strong low logic here. Strong mean we this GPIO pin is connected to the ground, that means through the NMOS. So we will get a low logic at the GPIO pin. But what will happen when we will write 1 at the input? So when it will be 1 here, at the gate it will be 0 because of this inverter circuit. So here it is 0. So once it is 0, NMOS will be in non-conduction state. In this case, what will happen? The drain will be not connected anywhere. It is floating. This is called floating state. So now our GPIO pin, which is going to the output, that is floating. It is not connected anywhere, neither low logic, neither high logic. So here actually the concept pull up or pull down comes into the picture. So if we want some certain state to be given to the output, so you won't prefer to keep it floating, like it can go to, this is called tri-state also, so it can go to any state based on some of the leakage current or some other factors. So we want to make it either high or low. So if it is open drain, if you'll see closely, then when we are writing it 1 logic, then our output pin is in floating state. We don't know what is the state of the output pin. So let us go to pull up and pull down. So pull up and pull down are concept used when the GPIO is in tri-stated or floating state. We don't know the state of the GPIO and we want one definite state to be applied to the GPIO. In that case, we can use some register. Those are called pull up or pull down register. So as we saw in open run condition, the output pin when we are applying a 1 or the output status is 1, it is in floating state. So similarly, when one GPIO is in floating state and we want a definite state to be applied, so in that case what we do, we either based on the requirement we add pull up or pull down register. So in this circuit, if you'll see, this button is here. So when we press the button, the GPIO is connecting to the ground. But when the switch is not pressed, so let us say this pull up register is not there. So in that condition, what would happen? The GPIO pin will be in some floating state. We don't know the definite state of that GPIO where it will be. So to overcome that, we add one pull-up register here. So when we are adding a pull-up register, it will pull the GPIO to the positive rail. Similarly, when the switch is configured such that the switch will connect the GPIO to the VCC or the positive rail when the switch is pressed, but when the switch is not pressed, now we don't know the certainty of this input, right? So if the pull down register is not there, then we don't know where the GPIO will go, whether to high logic or low logic, right? So to give a certain input when the switch is released, we add here one pull down register. So when the switch is released, it is not pressed, so the GPIO will be pulled down to ground. So it will be in a definite state of low logic. Okay, so when the switch will be pushed, so what will happen? The GPIO will be connected to the positive rail and will get a high signal. But as soon as it will release the button, it will be connected to the ground through the pull down registers. Okay, so on the right side also it is explained, it shows the same thing. So let us move to the GPIO registers. So as we discussed, based on the feature available for all the GPIO pins, we have different registers to configure those features. So here in STM32 we have 4 32-bit configuration register, and the first one is the mode register. So we can select the mode. As we see, the GPIO can be configured input, output, alternate function. So we can change the mode by writing to this register. Then output type. So again we saw the output type, that is whether open drain or push pull. So this output type we can select by writing to this register. We can change the speed, output speed, by accessing this register. Again, pull up and pull down. So we can set up pull up and pull down using this register. There are two 32-bit registers for input data and output data. Those are called input data register and output data registers. So as I told, so input data register, when we are reading something from the input pins, when some pins are configured as input and we want to read the input, then we have to access this register. And when we are writing something to the pin, output pin, so we have to access the output data register. Then bit set and reset register. So as we briefly discussed that bit set and reset register will allow us to access the output data register bitwise. So we can access each bit of the output data register by setting this register. We have the locking register, that is 132-bit locking register, where we can lock the configuration, so that if some bug is there in our program, it will not unintentionally change the configuration of the input and output. Then two 32-bit alternate function selections. So we can change the function of the GPIO pins and the port by accessing to these register. We have two 32-bit register, that is alternate function register high and alternate function register low. Okay, so let's have a glance of the structure of the IO port. So as we were talking already, we went through this. So this from this point, this is the outside, this is the pin, this is the IO pin, each IO pin. So each IO pin is having protection diode here. So if we got some transient or something from the outside, so these diodes will protect the circuitry inside the microcontroller. We have, as we were discussing, pull up and pull down registers. So pull up register is connected to the positive rail, and pull down register connected to the VCC. Now this pin is going inside, and the top part is the input driver, while the bottom side, this dotted line, is the output driver, and here is the analog. So if the pin is supporting analog functions, so analog will come here. Okay, so here whatever we already discussed about the push pull and open drain condition, this PMOS and NMOS is here, and this is the output control, which will have the inversion logic here, inverter, one inverter, and this is one mux which will choose the IO as alternate function or regular GPIO function. This is the output data register. This is the bit set reset register, and when we'll go on the input driver side, if you'll see, the pin is connected to here, and we have different function like analog. If we are using it for analog reading, ADC kind of thing, then we'll get here. This is the alternate function. If it is not alternate function, this will go to the input data register, and from input data register we can read the status of the input pin. So this is all these informations are taken from the reference manual. So you can just go to STM32L47 or the related reference manual, whatever MCU you have, and here we have everything in detail. So whatever I showed, that was just summary. So let us go here and see. So as we are seeing, these are the features, then GPIO implementation, and this is the GPIO function description, functional description, and this is the circuit whatever we just discussed, and this is the table which will tell, means if the mode register is configured as 0110 hurdle. So if you'll see, if the mode is 01, it is output. If it is 10, this is alternate function. If it is 00, this is again input, and 11 is reserved. So when we see the output type here, so if it is 0, it is push pull, that is PP. When it is 1, it is open drain. Okay, so speed, if you'll see here, we can configure at 1 or 0. Then this is pull up and pull down. If it is configured at 0, it is no pull up, pull down. If it is 00, no pull up, pull down. If it is 01, this is pull up. If it is 10, it is pull down. 11 is reserved. So similarly, we can configure the register and we can set up the IO based on our requirement. Okay, so we can go in detail with this reference manual. You can have a look. Now, as we have already discussed all the GPIO features and the related registers, let us go ahead and create a program to use the GPIO as input. So as we did last time. Let's go to file new STM32 project. Here it will initialize the target selector. Then from the board selector unit, we need to go Nucleo L476 RG. Select the board from the right side, click next, give one name to the project, let us say input button, and click finish. So it will ask initialize all peripherals with the default mode. Yes, as we are using one standard board, we can initialize all the peripherals as default mode. Okay, it will load the IOC file, that is the IO configuration file. And here it is. Okay, so we need two pins. One is the output, that is port A5, and port C13. So currently port C13 is configured as a GPIO external interrupt EXTI13. We'll use it as a GPIO input, normal GPIO input. So configure it as a GPIO input, and we'll go to system core GPIO. So here if you'll see port C13 is listed, and as we discussed, for input, pull up or pull down is very much necessary, otherwise the input may go to any trusted state and it will behave which we don't want. Okay, so if you'll see here, no pull up is applied. So what we'll do, we'll configure to apply as pull. So the button, when it is pressed, it connects the IO pin to ground. So in this case, we have to give pull up. So we have to apply pull up. User level, let us write. We have the flexibility to give some user level. So let us see push button or button. It will be better push button. Push button. Okay, and Control S. So it will generate the code. Yes, we'll change the perspective. Okay, so the code is generated and it will configure. If you'll see, it is configured. So UART is configured. We will not be using UART in this video today. And here is the configuration of GPIO. So GPIO is initialized. So LD2 pin that is connected to the LED, and here if you'll see push button, this is connected to that is port C13. Okay, so we gave one user level to that pin, and it came here push button pin. Okay, so we'll be using LD2 pin here, and this push button pin. These two, push button is the input and LD2 pin is the output for us. Okay, so as we did last time, the drivers, so STM32L4 driver, go to include. This we are doing to see the available APIs, HL APIs, and go to HL GPIO.h. So from here we'll get the name of the APIs. So if you'll see, these are the APIs we'll be using. HL GPIO read pin. So this is one. So what we'll do here in our program, Control C, let us Control C, go to the endless loop. This is the infinite loop, and we need to write our program here. What we'll do, if the button is pressed, that is Control V, if the button is pressed, it will read the pin. Which pin? Our push button pin. that is this is push button GPIO port. This is the port where the button is connected. So copy here and just paste over here. Again, go and push button pin. So okay. So in this if condition, we will be checking the pin status that is connected to the push button. If it is high, that means the button is not pressed. Will be writing low to the output. So let's copy here, Control C, and here Control V, and let us copy our name of LD2 port, that is LD2 GPIO. Control C, and here B. This is LDIO2 pin, sorry, LD2 pin, and here to know the states, click here, control and click, and we will be resetting it. So copy, Control C, we will be making it low when the button is not pressed, that is the pin is high. So this is GPIO pin reset. Okay, so let us copy the whole thing again for the else loop. Control C, else, Control V. Okay, so when the button is pressed, it will go to the else condition and will be setting the pin, the output pin will be making it 1. Okay, so let us go ahead, Control S, then run the program. Okay, so finished building. Let us press the button, reset button, and it is connected successfully. So if you'll see, now the LED is not glowing, and this is the button that is connected to the port C13, pin number 13, and we have configured as input. So once we press, yeah, so you can see the LED, that LD2, it is glowing when we are pressing the button. Okay, so here we learned how to set up one pin as input and take some action based on that input condition. So you can explore more on different configuration and experimenting different things using GPIO input and GPIO output. Till then, take care. Bye bye.